Okay. All of these things reduce everything, all problems, not the halting problem. The halting problem doesn't reduce the input checker. But all of the problems for which we can check a solution in polynomial time reduce the input checker. If we could solve input checker, we could solve all of these. Okay, now Cook's theorem is sort of, Cook's theorem says sort of input checker, so Cook's theorem. Reduces to SAT. Okay? We do not have a lot of time. Okay. So do you see that all of this stuff reduces to input checker? If I can draw this arrow, then it means SAT. If I can solve SAT, I can solve all of these problems. If I can solve SAT in polynomial time, I can solve all of these problems for which I can check a solution in polynomial time, because we believe that for input checker. So if we reduce input checker to SAT, then we're done. Okay. Then SAT is NP complete. It means everything for which you can check a solution in polynomial time, if you can answer SAT, you can answer those problems, all of them. And that means if you can answer for colorability, you can answer SAT, so you can answer all of these problems. Okay. Now, what we're going to, I was trying to think of exactly how to phrase all of this. And then I managed to go and get it wrong. Okay. So we sort of know how a computer works, right? I mean, you've got these registers and stuff like that, and so you have some memory. Let's pretend that the memory is you're allowed to use polynomial memory. So given an instance, you're allowed to like malloc some huge amount, polynomial amount of memory. And then you're allowed to run in polynomial time. So what we're going to want to do is write, so you have the program has to run in some time bound. And you want to write a formula that's satisfiable if and only if there's an input to this program that makes it say yes. People following? 14 people. Okay, so this is the reduction. The idea is to reduce input checker to SAT. Given some program, we want to write a big formula, but polynomial size, and it's going to say it's going to be satisfiable if and only if the program runs on, for some input, the program is going to run and say yes in polynomial time. Now, what you're going to do is for every bit in the memory, so you have polynomial memory. For every bit in the memory, you're going to have, actually you're not just going to have one variable. For every bit in the memory and for every time step, you're going to have a variable xij if bit I is 1 at time step j. Okay? And then what you're going to do is imagine that you have like your little control unit, your CPU. Okay, so, and you have this polynomial size memory. If the CPU is looking at, well, let's say the CPU is not looking at a bit, then if the CPU, so you have some like some pointer which is saying what the CPU is looking at right at the moment. If it's not looking at a bit, then the bit is the same in time step j plus 1 as it was in time step j. So you have to write a formula for every bit and every time step. You write something saying, okay, if the contents, like the pointer in the CPU, is not to this memory address, then the bit is true if and only if it was true on the last time step. Okay, it didn't change. And then you say, okay, if the CPU is looking at some word, machine word, and then you have to go through and say, okay, what can the CPU can be doing? So, you know, you have the contents of, what is it? Contents of the address register, contents of the decrement, blah, blah, blah. Like, however your CPU is built, you can sort of think of it as like a little finite state machine, but, you know, except it has these registers. But it's like finite memory. So, you know, you have this model and it says, okay, this word is storing what other word I'm looking at, and if this is, you have the bits in this, and you set all of it. This is hugely annoying, okay? Like, you'd never actually want to do this. But you can think about it as like our computers are just circuits. Like and circuits are equivalent to Boolean formulas. So you could actually build a circuit that's it's only going to touch polynomial space, and it's gonna compute the contents of every bit for every time step. And so how big is it going to be? Well, it's going to be polynomial time steps, polynomial bits. It's all going to be polynomial. So yes, you could write a big formula that is true, that sort of simulates that takes, and then you say, okay, and then you have the input bits, the contents of the initial contents of memory. And you say, is there some initial contents of this input string that makes the formula true? Well, yes, if and only if you can set these variables to make the formula true, if and only if you can set the bits in the input so that the program is going to accept. Okay? That's the informal version. It can be made formal. Okay? We don't have a lot of time, so do people sort of get this? I hope it'll be better in the lecture notes. So yeah, the idea is your program is only going to run, if it's going to run in polynomial time, it can't touch more than the same amount of the polynomial memory. So you can describe sort of the contents of that memory and all the time steps with a big formula that says it behaves properly. Your program executes like this. And the formula is going to describe how the program executes. Now, so that's Cook's theorem, is saying input checker reduces to sat. Okay, so that means all of these problems, if you can solve any of these, any problem for which you can check a solution polynomial time, you can find a solution polynomial if you can solve any of these. We don't think that's true. We think probably you can't solve any of these in polynomial time. But we can't prove it. Right? So it's been open now for 50 years. And this is like considered one of the 7 big problems. I mean, some of them are now closed, but in the year 2000, this was considered one of the 7 big problems of mathematics. Remember I was going about Hilbert and the problems for the 20th century? There were 7 problems chosen for the 21st century, and this was one of them. It's like, okay, are any of these actually possible in polynomial time? And so, actually, the question asks for a proof that they're not, because nobody really thinks they are. Although, until there's a proof. Okay, so, I wish I could do that. I wish I were doing this more formally, but I should have slept. Okay, just in the last 15 minutes, I'd like to talk about Turing machines, okay? Because usually, so Cook's theorem is actually about Turing machines, because everybody uses Turing machines. So he doesn't talk about C programs. He talks about, does a Turing machine halt? Is there an input for the Turing machine such that it will halt and accept in polynomial time, blah, blah, blah. But C programs. I mean, you've seen them, even if you don't program in C, but you may not really be familiar with Turing machines, because you've probably never seen one. And a lot of people have probably never written a program for one. So there's a reason for that, which is Turing machines became popular because back when Turing did this stuff, we didn't have we certainly didn't have electronic computers. We didn't really have we didn't have electronic computers. We didn't have mechanical computers, really, sort of ish. So he was, if you've seen The Imitation Game, yes, he was helping build an electronic computer. So most people had never seen a machine that did computations. So if you said computer, it was a person, okay? Like in that movie Hidden Figures. If you said calculator back then, it was a person. The people who did the calculations that sent people to the moon, sent people in orbit, wherever. So in order to talk about what a computer could and couldn't do, you had to come up with a formal model of what is a computer. I think it's where Turing came up with the notion of the Turing test. He actually talks about okay, well, what if people have extrasensory perception? How could a computer compete with that? Okay, so he was really trying to cover sort of all the bases. Oh, cool. Because he wanted to say there are certain things that computers cannot do, which we'll see at the end of the course in the diagonalization and the halting problem and Kolmogorov complexity, all that kind of stuff. But he wanted to prove that there are things that computers can't do. In order to prove what a computer can't do something, you have to know what a computer is. So you have to come up, in order for people to accept your proof, they have to believe in your definition of a computer. Because actually there was something which is equivalent to Turing machines, which is Church's lambda calculus, and that really wasn't as widely accepted until Turing came along and did Turing machines, and people said, yeah, okay, if it can be computed, it can be computed by one of these things. And I have 15 minutes. So, but you have grown up with computers. I am talking to you on a computer. You have computers sitting in front of you, you have them in your pocket, you have them on your wrist, you're surrounded by computers. It's not like this is 100 years ago where you don't have an idea of what a computer can do. You believe me that if I can't do something in C, then it's probably hard, right? If I can't write a C program to do something, then it's, you sort of, yeah, okay, it seems like a computer probably can't do that. You don't think well, maybe there's a more powerful programming language, or maybe there's a more powerful computer architecture, or something like that. Yeah, okay. You'll just sort of, for third year, this is enough. You believe me that if it can't do it in C, that's a pretty strong statement. So, but Turing had to say, okay, what does it mean to compute? So he said, imagine a little person, and they've got a desk, and they have a pile of papers. And what can they do? So this paper is squared papers because, we're mathematicians. And they can, or actually, you think, well, okay, you can take the paper and cut it and make a big ribbon. Okay, so it's infinite in both directions. You have squares, and you have a pencil with an eraser. And in each cell, you can write a symbol, you can erase the current symbol, and you can write a symbol from some fixed alphabet. So 1, 0, hash, something like that. So it's fixed. It can be it doesn't actually matter the size, because of course if you make it 5 times larger, well, I can just use more cells to represent. I can still use binary and just if I want 256 characters, I can just use binary and make it 8 bits. Except I need a hash. So it doesn't really matter what the alphabet size is, as long as it's not unary or something silly. And he said, okay, so what can this person do? Well, they can erase, they can write, and they have some sort of finite state control. Like they have a finite amount of memory in their head, right? So what you can think of is you believe in what a computer, like you know what a computer is. Imagine that you had a computer with some fixed amount of memory, possibly large. I mean, 2 to the 64 bytes, right? So how much is that? 2 to the 64 times 8 is very big. So it's 2 to the 67 bits, but it's finite. Right? Now, it's not connected to the internet or anything like that. What it has is a tape drive. If you've ever seen a tape drive. I think people still probably don't use them anymore. And so what it can do, it can view a little cell on the tape, and it can, this is actually plausible, it can change it from a 1 to a 0. It's, you know, I think they still use these big platter, big tape. They used to. I've seen them. Probably not anymore. So you think, okay, what can it do? It can read, and then if it runs, if the tape, it can run the tape forward or it can run the tape backwards, and if the tape sort of runs out at one end, then somebody comes in and changes that. Okay, what can it compute? Well, you think, okay, it's a finite state control. It's got a finite amount of memory. A lot, but it's finite. And it's got this tape that's infinite in both directions, because whenever it runs out, somebody comes in and puts a new tape on, or, you know, when it gets in, if it's an old tape, then they sort of have a stack of like, okay, this is the ones on this side, this is the ones on this side. You think, what can it compute? Why do we need this model? We don't anymore. But it's people, if people say Turing machines and you say, I have no idea what you're talking about, and they'll be, oh, you didn't study theoretical computer science. You can use C. I mean, we can actually show that, you know, sort of whatever you can do with C, apart from the fact that C has like bound pointers, but if you can deal with large pointers and the stuff, and the C can do anything a Turing machine can do. How do you know that? You can program a Turing machine in C. So how do you actually think about a Turing machine? Well, you have this tape, and it's a finite, it looks like, you've seen finite state machines, but for every arrow, so for every state, you say, I'm in state whatever. I think it's a quintuple. What state are you in? If you see this symbol, what do you do to the tape? You change that symbol, do you move left or right? Okay, and which state do you go to? So it's like you've seen transition functions for finite state automata. So this is a bit more, normally for a transition function for finite state automata, you just say, okay, if you're in this state and you see which character, which state do you go to? This one is saying, if you're in this state and you see this character, what do you write? And do you move the tape left or right, or do you leave it in the same position, and which state do you go to? Okay. I'm not going to make you program Turing machines. People made me do that, but I think it was a waste of time. So you can see, instead of input checker with a C program, you could do input checker with a Turing machine, right? Because, what do you have? You have a variable that says, okay, in step whatever, I'm in state this. In step whatever, cell whatever on the tape is a 1, cell whatever on the tape is a 0. Right, it's the same. So, that was really quickly, Satan's transform will be in the lecture notes. This will all be in the lecture notes once I get this paper out of the way, and some other stuff that I have to do this week. The key thing is this, you see that input checker is very powerful, and Cook's theorem says that input checker can be reduced to SAT, and the idea is to show that something else is also in this class. Now we get to the point where I tell you why nobody ever sees those, like, Can you reduce clique to sat? Yes, of course, nobody reduces clique to sat, okay? Why? Because to show that something's in NP, I wanted you to see that you could reduce it to sat to sort of get the feeling of how to write a formula that says, that sort of expresses a problem, that says this problem can be, this formula is satisfiable if and only if this problem can be solved. Because that's really the essence of Cook's theorem. Once you sort of know, you can see that, yeah, I could write a program that sort of does, that input checker reduces to sat. So I want you to understand that sat is that powerful. But if somebody gives you a problem, somebody suggests some problem. Okay, like 3-person canoes. Okay? I mentioned that on one of the assignments of the midterm, you have this thing about putting 2 people in canoes. And you could do that. And I think I mentioned somewhere that if you can fit 3 people in a canoe, so not everybody needs to row, then the problem is NP hard. It's actually NP complete. 3-person canoes. So given a bunch of people and how much their equipment weighs, how many canoes do you need if you can put 3 people in a canoe? Okay, so this is actually a problem called 3-partition. To show that it's in NP. Before we were reducing it to sat, but now we just have to reduce it to input checker, which means we just have to say, can we check a solution in polynomial time? So that means if we can check a solution in polynomial time, then it reduces to input checker. So it's at most as powerful of these. I mean, some problems like sorting. Sorting, you can reduce it to input check. Well, okay, sorting is not a search problem, is not a decision problem. I don't know, like minimum spanning trees. You're given a graph and some integer k, and you're asked, does this have a minimum spanning tree with a cost of most k? Right? That can be reduced to input checker. Clearly, you can check. Like, ooh, is there an input? Yeah, somebody gives you a spanning tree. You can check if it has at most the desired cost. So there are things which reduce the input checker which are not sort of equivalent to these in that we can solve minimum spanning trees in polynomial time, but it doesn't mean that we can solve SAT. So what we've got is 3-person canoes, and then we have to choose one of these other problems. Like suppose, I don't think you actually do this reduction, but suppose you could take vertex cover and show that vertex cover reduces to 3-person canoes. And be like, yeah, okay, then 3-person canoes is NP complete. So it's sort of equivalent to all of these. So now you can forget about, except for maybe the midterm or something like that, you can forget about how to reduce, how to take a problem and turn it into a SAT formula. Because people don't do that, they just say, oh, is it in NP? Is it possible to check a solution in polynomial time? But to understand Cook's formula, to understand Cook's theorem, I think it's useful to see first that you can reduce things to SAT, to practice a couple of them, and then say, okay, well, you can reduce this insanely powerful thing to SAT. So now you don't have to reduce things to SAT, you just reduce them to this insanely powerful problem, and that reduces to SAT. So yeah, everything for which you can check the solution is reduces to SAT. Probably I'm down to 12 people, but I still have 4 minutes. Are there any questions? This is going to be fun to write as lecture notes. So, I mean, so yeah, like Cook's theorem, like SAT is NP complete, and this thing about everyone says like, how do you show that something's NP complete? Ooh, you have to show that it's in NP. You often, people frequently forget to show that it's in NP. It's like, yeah, okay, you have to show, if you think about it as being like part of this, you can, how do you show that 3-person canoes is sort of in this equivalence class? Well, you have to be able to get from 3-person canoes to one of these, and it's usually this one. You can check it, well, it's always this one. You can check it in polynomial time if you're given a solution, and then you have to get an arrow from one of the others going here. And there are hundreds of other problems. So it's really useful if I can get it out before the midterm, which is next week? Next week. So yeah, I'm going to try to get it done this week, but I owe some administrative stuff. I owe this paper. Sorry about messing up this. Like, is there an input to P? Yeah, that's the important thing. So you have to be, it's easy as you do that. I'm going to, as soon as possible, but that's may not be super soon, but in the next few days, I hope. I know what I want them to say. I just haven't got time to sit down and type them up. It's supposed to rain for the rest of the week, but they've been saying that for days. So every day I think, ooh, it's going to rain. I don't want to go outside then, and I'll get it's 5th of July. What's 5th of July? Yeah, the midterm starts on the 5th of July and ends on the Friday. So there'll be 5 questions again. Probably 3 dynamic programming and 2 NP completeness. Okay, we have less than a minute left. I'm going to stop this recording. Stop recording. Ding.
Recording stopped.
Okay, and then I'll stop this.